So here we're going to just take a brief look at the structures that comprise the phyllosilicates. These are the silicates that are made of sheets or layers. This fellow over here, the first thing we're going to look at is this so-called octahedral sheet. It's a very important building block for the phyllosilicates. When taken alone, we don't get a silicate. There's no silicon here in the cations that are being listed in this diagram by Klein and Dutrow. Instead, we have a layer of magnesium or aluminum atoms that make up these central cations there, and there. And they're surrounded by a layer of OH here. So all of these guys here, those are OH. Another layer of OH up here as well. So we have OH, and then some magnesium atoms. We'll just take the magnesium case and another layer of OH atoms here. So we don't really get a silicate in this case, but we do get a layer of octahedra. 4 of those octahedra are shown here. And if we take these octahedra layers and just repeat them, if we took another bunch of octahedra and put them over here and then continued that indefinitely, then we would get the mineral brucite, at least if we take all of the central cations to be magnesium. Brucite has the formula Mg3OH6. We usually write it in 1/3 of that amount, but we're going to use the 6 oxygen bases, as you'll see, for writing other formulas and making comparisons in a moment. If instead we filled up all of the central cations with aluminum, aluminum has a 3+ charge, so for every 3 magnesiums, we would only need 2 aluminums to provide the charge balance for 6 hydroxyl units. So we would have the mineral formula Al2OH6, and that is the mineral of gibbsite. These are not phyllosilicates per se. They're not really silicates because there's no silicons involved, but these are important minerals in the clay family, and they're built up of just repeating these octahedral sheets here over and over and over again. Now, the other kind of sheet that can be interlayered with these octahedral sheets are the tetrahedral sheets. And again, shown here, tetrahedral. Let's write out. This is another diagram from Klein and Dutrow, as are these over here. So a tetrahedral sheet is made up of Si2O5 units. The silicon all have a +4 charge, so we have a total +8 there of cations. The oxygens are 2-, so that gives us an overall charge of 2-. And we'll see how that comes into play a little bit later on. For shorthand, we're going to call the octahedral sheets O, and then the tetrahedral sheets we'll simply call T. And then you can imagine linking these up. So here's a case where we have a tetrahedral sheet here and an octahedral sheet here, and we can repeat those over and over again. We'd call those a so-called TO structure, where the structure would be TO, and then another TO, and then another TO, and then each of these would be bonded together by van der Waals bonds. And then we have the so-called TOT layering, so that's an example here, where we have a T, and then an octahedral sheet, and another tetrahedral layer here, making this triplet of TOT layers. This is the top of another TOT layer here. And so instead of having a series of doublets here, we would have a series of triplets. And again, they would be linked by van der Waals bonds. In a moment, in another video, we'll take a look at the formulas that pertain to these. But when we talk about those mineral formulas, we're going to spend a lot of time talking about these tetrahedral and octahedral sheets. And you might want to come back to this video to remind yourself what we're looking at in terms of the larger structure of these phyllosilicate